Hey guys, this is Mr. Marshman, and we're going to talk today about rotation. And so, up to this point in this course, we've really only talked about objects as being sort of these dots. It hasn't been super realistic. If we had some some ball, let's say, that was rolling, we really talked about that ball as being simply, we could replace that ball with a simple dot and say, oh, the dot is moving in this direction. Is that very realistic? Not really. Or if we threw, um, let's say, a bowling pin, right? If we threw a bowling pin in the air. That's a terrible bowling pin. We could really just say, hey, the bowling pin is represented by this dot as the dot sort of travels in this parabolic path. Now, in this chapter, we're gonna make things a little bit more interesting. We're gonna start to treat objects as rigid objects, and we're gonna be able to talk about um, their movement in terms of their rotation as well as their translation. And so, in the past, we've talked about this idea of kinematics, and that's really, we've talked about really linear motion of objects in a straight line. We talked about terms like displacement, velocity, and acceleration. In this chapter, we're going to look at rigid objects, so things like wheels and discs and things like that, that are rotating. They can be moving as well. They can be moving, and sort of this wheel could be moving in this direction as well. But as it moves, it's going to be rotating, and so we're going to talk about what sorts of things can we describe about that motion, and how can we use physics to talk about that. So here we go. Let's go ahead and dive right in. In order to really set a background, this video is going to really talk about three terms. We're going to look at these terms: displacement, velocity, and acceleration, and sort of see how we can use those terms and how we can use those terms in this rotation chapter as well. So first things up is angular displacement. So in linear motion, we talked about displacement, where we could look at the initial position of an object, look at the final position of an object, and that would tell us sort of what its displacement was. And that was really motion that was in a straight line. So if you think about this as being sort of xi and this being xf, the displacement is just the difference between those two positions. Well, what if the object itself isn't actually moving, but it's simply rotating? So imagine a CD or a DVD that's rotating around in a circle around this sort of fixed axis of rotation here. Well, if it starts off here, let's say I'll look at this point on the CD. There's a scratch or a dot on the CD. As this disc rotates, this dot is going to move along the CD, right, as it rotates, and it may end up here. Well, it didn't travel in a straight line. It actually traveled in this curved path. I can describe the angle at which it moved, the angular displacement, in terms of the final angle minus the original angle. And by convention, we always describe the origin. Here we'd have to label some origin up here if we're talking about linear displacement. Here we typically refer to the origin as being this sort of like this 0 degrees or 0 radians. And so the initial would be 0 for this case, in this dot, and it would have rotated about this far, and so we'd have some sort of final position, or theta sub f. That would tell us how far it has rotated, as angular displacement. Now, the units we use for angular displacement are the radian. So we could use degrees as well, but the one that works the best for physics is the radian. And what a radian is it's a relationship between the arc length, which is this length of this arc here, and it's the ratio between that length and the length of the entire circle, so the circumference of the circle. And so, speaking of arc length, we can describe arc length as S. All right, S is equal to the radius, or how far the object that we're interested in is from the axis of rotation times the angle. So this length, if I'm talking about the arc length that my dot traveled, is equal to r, which is the distance from the axis to this point, times the angle that it swept out. The arc length of a second dot, sort of on the edge here, the arc length would be a little bit longer, wouldn't it? Just simply because the radius is greater. The angular displacement is the same for both dots. And what this tells us is how far or how much an object has rotated about its axis of rotation. And so in this case, if it had rotated, let's say it rotated, pi over, what is that, about pi over 4, let's say, pi over 4 radians, then we'd say the angular displacement, since it started at 0, it ended at pi over 4, the angular displacement is pi over 4 radians. I typically write in the radian here. You don't have to, but it reminds me that I'm using radians and not degrees when I'm doing this. Let's talk about angular velocity. So angular velocity is simply how quickly that angular displacement is occurring. So how quickly the object is rotating. And it's measured in radians per second. So how many radians am I sweeping out? How many radians am I sweeping out per second? Typically, we refer to the direction, because when we had normal velocity, we typically refer to sort of the right or up as being positive, down and left being negative. Here, we don't really have left or down because those sort of perspectives change as you rotate. So we refer to the counterclockwise direction to be positive and the clockwise direction to be negative. And that's just sort of how we do that. We can also describe omega as being, a sort of a simpler definition is 2 pi divided by the period. If you remember back to a couple chapters ago, the period is just the time it takes for one complete revolution or one complete rotation. And so since 2 pi is the angular displacement after one complete revolution, 2 pi divided by the period makes sense to be the angular velocity. The symbol we use for angular velocity is omega. It looks sort of like a W. It's the Greek letter omega. And the units we're going to use are radians per second. Okay. Now, one thing to keep in mind that's sort of interesting about angular velocity is that if I pick some point, let's say I pick some point on a rotating disk. Let's say I pick point A and point B. So I got point A and point B. As this disk rotates, point A and point B have the exact same angular velocity. Since they're on the same radial, they're on the same line here through the axis of rotation, they actually both rotate at the same speed. The time it takes for A to go all the way around is the same as the time it takes for B to go all the way around, right? Because they're on the same disk. Imagine they're on some sort of record player that's revolving, right? They're going to go around in a circle the exact same amount of time. So the angular velocity is going to be the same for both of these. However, their motion is very different, and so we can think about the actual speed, the tangential velocity, which we denote VT. Tangential velocity is the actual speed of the individual particle. Those are very different. If you think about if A represents like a ladybug on this disk, the wind that's going through ladybug's little hairs is going to be much greater when it's further out than when it's further in. Hopefully that makes sense intuitively, but here's why. Ladybug A, to undergo a displacement from here to here, right? The time it takes to undergo that displacement is equal to the time it takes for B to go from here to here. Yeah. Now, of course, that is the same angular displacement for both of these, so that's why they have the same angular velocity or rotational velocity. However, The arc length, the length that A travels, is much less than the length that B travels. B has to travel this huge length here in that same amount of time. Therefore, the tangential velocity depends on the distance r from the axis of rotation. So the tangential velocity of B is greater than the tangential velocity of A, although they have the exact same angular or rotational velocity. Now, one really helpful thing with angular rotational velocity is comparing it or being able to connect it with the velocity of an object's center of mass. So, for instance, when I'm talking about it like a wheel or something rolling without slipping, so the key here is that it's, that as it rolls, it also moves. There's no skidding out or anything like that. So, for instance, this tire here. As this tire is rotating, the car and the wheel are moving to the right. Well, the speed at which the translational velocity, that's v, the translational velocity, is equal to r, which is the radius of the rotating object, times the angular velocity. Let's see what, sort of why that's true. If you imagine this tire has a dot right here on it, let's say. And actually let's make it right here, right where the tire hits the ground. And that dot, and let's see when this thing undergoes one complete rotation. So by the time the car is moving to the right, the wheel rotates one complete time around. That dot, let's make it there, is going to end up somewhere over here when it hits again, right? Oh, I'll keep making this. In other words, it's going to have traveled some sort of distance, delta x, let's say. That distance is just simply the circumference of the circle, which is 2 pi r, correct? Because it now has unrolled or rolled one complete revolution. So it's 2 pi angular displacement times r, which is, so the arc length is 2 pi r. Well, 2 pi r over t is going to give me the time it took to complete one revolution will give me the tangential velocity, which we learned back in our circular motion days. Well, vt is equal to 2 pi r over t. Vt is also equal to that, and so we can relate those two things to each other. Let's look at a couple examples here. We're going to calculate the angular velocity of a 0.3 meter radius car tire when the car travels at about 15 meters per second. Okay, so let's take a look. So we just saw this relationship that the velocity of an object that's rolling without slipping is equal to r times omega, or we can write that as omega equals the velocity divided by the radius. Since we know those two quantities, velocity and radius, we can say that omega equals 15 divided by 0.3, which should give me 50, and my units are going to be radians per second. Just really quickly, notice what happens. Notice what happens to my units here. I have 15 meters per second divided by meters. That should give me 51 over seconds. That goes to show you that this radians here is really dimensionless. We don't really need it. Dimensionless. We don't really need it in there. We could just say 51 over seconds. However, I like to include it simply because it helps remind me that I'm using radians as my sort of rotational angle measure, not degrees. So you're welcome to not include it. I typically will. Let's look at the second part here. It says, would the angular velocity be if the radius had been 1.2 meters instead of 0.3 meters? So let's just see what happens here. What would the angular velocity be if they had the same speed but larger tires? Well, the angular velocity would be 15 divided by 1.2, which should give me, I believe that's 13 radians per second. Oops. Let me go back up. Okay, so it should be 13 radians per second. All right, and then our last thing that we're going to talk about is angular acceleration. Angular acceleration is super important in this chapter, similar to how translational acceleration was very important sort of the first half of this year. But angular acceleration is going to describe the rate of change of angular velocity, so how quickly the angular or rotational velocity is changing. Is it rotating faster? Is the rotation getting faster, or is the rotation getting slower? And it's given by the change in omega over the change in time. Now, if something is rotating, it can have both tangential acceleration and it can have centripetal acceleration. Right? We've talked centripetal acceleration being the acceleration that keeps it moving in a circular path, always directed toward the center. But it can also have this acceleration tangentially. And tangential acceleration can be described as r times alpha. So how for point P on the wheel here, point P can have an acceleration inward, which is equal to centripetal acceleration, which is v squared over r, right? Which is what we learned last in the circular motion chapter. It can also be, if this wheel is speeding up, then point P is actually getting faster and faster and faster as it rotates. It can also have tangential acceleration. That can be described as r times alpha. Well, when we're doing rotating things, sometimes it's easier to write everything in terms of rotational variables, and so we can actually write centripetal acceleration in terms of those variables as well. All we need to do is recognize that this v can be written as r omega, right? V tangential velocity is r omega, and so doing some algebraic manipulations, we can see that centripetal acceleration can also be written as omega squared times r. And that might be helpful down the road, so just wanted to show you guys that. So let's look at two examples, or one more example, and then we'll finish up here. So here we have a bear riding a unicycle. If the unicycle wheel begins at rest and accelerates uniformly in a counterclockwise direction, so let me just draw this out real quick to get a better view of what's happening here. So here's our wheel. It begins to rotate in a counterclockwise direction. So omega is heading that way. It accelerates to an angular velocity of 15 RPMs. RPMs is a common measure of, it means revolutions per minute. So it's a common omega or rotational velocity measure. It's not the one we like to use, but it's very common to see it that way. And it does this in a time of 6 seconds. So we have an initial omega, which is 0. We have a final omega, which is 15 RPM. And we have a time at which that change occurs of 6 seconds. So let's go ahead and do this. Let's look at, so alpha is change in omega over time. So alpha is 15 over 6. And so that gives me alpha equals 2.5 revolutions per minute, so RPMs per second. Does that make sense? Now I might want to write this in terms of sort of my standard units, which is radians per second. So let's convert this into radians per second, or radians per second squared. So here's how I do that. 2.5 RPM, which is really, let me do that. So that's revolutions per minute per second. So I've already got my per second on the bottom, so I'm good there. So what I might want to do first is convert revolutions per minute into radians per second. Well, revolutions, so 1 revolution per minute is the same as Yeah, this is, oops, sorry. 1 minute, 60 seconds. And then 1 revolution is 2 pi radians. And so what I need to do to get this into radians per second is to simply multiply that times 2 pi and divide by 60. So and that gives me 0.26 radians per second squared. Okay? So let's finish this up. Let's talk about the relationships between linear or translational motion and angular motion and how we can sort of connect the two. So displacement. Displacement was given by delta x in our translational motion. In angular motion, it's given by delta omega. Delta x and delta omega. We can write the relationship between the two as essentially the arc length, which is equal to r omega. Okay. S, or most of the time we can just write it like this: delta x equals r omega. Translational velocity was v, right? Here it's omega, which is delta theta over t. Here this was delta x over t, right? The relationship between the two was v equals r omega, right? And when something is rolling or something without slipping, we can write them like that. That relates those two quantities here. Here, acceleration is written as change in velocity over time. Here, angular acceleration is the change in angular velocity over time, right? And so the relation between the two, we can write the tangential, right? Very important to write tangential acceleration equals r alpha. Tangential acceleration equals r alpha. And we also can say the centripetal acceleration was omega squared r. Sort of interesting connection there. Translational time, which is t. Hey, look, it's the same time that we've been using before. Okay, so we're going to use these a lot coming up. And so just to make sure we're all on the same page, let's do a little concept check to finish this thing up. Bonnie sits on the outer rim. Clyde sits midway between the center and the rim. The merry-go-round makes 1 complete revolution every 2 seconds. How do their angular velocities compare? Their angular velocities, how do they compare? Well, their angular velocities, since they're sort of sitting along this radial line together and they're not moving at all, they're sort of staying, they're not sliding along the surface, they're rotating around together. They have the same exact angular velocity. We can see that is choice 1. The angular velocity is the same on a solid object. They both go around 1 complete revolution every 2 seconds. Who has the larger tangential acceleration? Let's go back and look at that. Follow up. Who has got the bigger tangential acceleration? Hey, that would be Bonnie. Bonnie has a, going the other way. Bonnie has a greater tangential, well, actually, they have the same tangential acceleration as long as they're not speeding up or slowing down. Which one has a greater centripetal acceleration? Interesting. Which one has a greater centripetal acceleration? Well, AC equals omega squared r. They have the exact same angular acceleration, or sorry, angular velocity. So the one with the greater radius has the greater centripetal acceleration. So Bonnie here would have the greater centripetal acceleration. Their tangential accelerations are 0 for both, since they're not speeding up or not slowing down. Okay, well, I hope this was informative. I look forward to hearing any questions you guys might have. Good luck, and I will talk to you guys soon.